This is Daniel Cusberry, and we are still looking at some basic introductory concepts in probability. And we're looking at complements in this video, and complements are really handy tools once you learn how to use them. I really like complements because they tend to make problems easier as long as you remember what they are and how they operate. And so I'm going to show you just a few tricks in this video revolving around this idea of complements. Let's look at this example. If there is a 60% chance of rain today, then we know that there's going to be a 40% chance that it will not rain. The events rain and no rain are called complements. So this is the definition. The complement of an event says that the event does not occur. So this is just a really straightforward, really basic. Either it's going to rain or it's going to not rain, and there's nothing else in between. So to say that something's a complement of something else, then you would use things like the word not or no, like it just doesn't happen. So if A is an event, the complement of A is the event that it does not occur. So it either occurs or it doesn't occur. The complement of A is denoted by A with a little c. So you've got A and you got A complement. It's either happens or it doesn't happen. And what's useful about complements is if you imagine your sample space being this big little circle blob here, this is my sample space. And let's just say that A takes up a special part of your sample space. So maybe A is like right here. And anything that falls in this blob can be event A happening. Well then, if A doesn't happen, then it's going to end up outside of that blob and end up making up the rest of your sample space. This, for instance, let's say A is it raining and A complements it not raining. What we've done is we've divided the whole set of possible outcomes into two specific things. Either it rains or it doesn't rain, and there's nothing else that can really happen. Well, you might say, well, it can snow, but yeah, but we're saying it can rain or it doesn't rain. If it snows, it didn't rain. It's either raining or it didn't rain. So true complement divides the sample space into two parts: the actual event itself, and then the event that it doesn't happen, which is called the complement. This is really handy, and I'll show you why in just a minute. But let's look at some complement examples first. We've got 200 students enrolled in a stats class. Here's a stats example. Haha, we're all in stats class. Find the complements of the following events. So the event A is exactly 50 of these students are business majors, and I want to find out what A complement is. I'll try to write well this time. A complement is going to be that this doesn't happen. In other words, we want to say that there aren't exactly 50 of them that are business majors. So maybe I could say the number of business majors is not 50, or something like that, where you can see that it's either going to be exactly 50 or it's going to be not 50, which means it could be 1 through 49 or it could be 51 to 200. But the point is, a true complement is going to be exact opposite, or opposite may not be the best word, but it's going to be A not happening. So if A doesn't happen, then this thing has got to be true. It's not 50. The number's not 50. So let's look at this one. B is the event that more than 50 of these students are business majors. So I want to find the complement. So if more than 50 of them, that means there could be 51, 52, all the way up to 200. So I want to describe the complement of this event, which means it can't be 51 or 52 up to 200. It's got to be less than 51. And my question is, can I put 50 in the complement? If this says more than 50 of them are business majors, then if I have 50, it's not included in this event B. It can be in the complement. Let me go ahead and write this down and see if that makes sense. So what I can say is 50 or less are business majors. It's like writing every other letter. Okay, so let's make sure these are true complements. So if it's a true complement, there can't be a number in both of these. This has got to capture some of the numbers. This has got to capture the rest of the numbers. So more than 50, that would be 51, 52, all the way to 200. 50 or less would be 50, 49, 48, all the way to 0. Yeah, it could be 0. So this is a true complement because we don't have any numbers that are in both of these things. They're either this one's going to happen or that one. They can't both happen. It's kind of like raining and not raining. They can't both happen. That's important. Let's look at C. C is the event that at least 50 of them are business majors. So that means that C complement has got to be the event that this doesn't happen. At least 50 means that there could be 50 or there could be more than 50. So whereas this one started at 51, 52, and so on, this one's going to start at 50 or then go up to 51, 52, and so on. Do you see the difference between saying more than 50 or at least 50? This doesn't include 50, this does. So since this includes 50, my complement cannot include 50. This is 50 and more. This is not 50 and more. So maybe another way to say that is less than 50 are business majors. You see, this has got to be really precise. So if I'm counting 50 here, then I can't count 50 here. But here I'm not counting 50, so I've got to count 50. The idea of the complement is that everything that's not in B has to be in B complement, and everything that's not in B complement has to be in B, and so on and so on and so on. So like here, this is the number 50 is in here, but 1 through 49 and 51 to 200 is not in here. So that's all those numbers are wrapped up in here. If it's not 50, it could be any other one of those numbers. All right, let's look at the rule of complements. Well, we're almost there. I wanted to review something first. So remember from a previous video, the introductory one for probability, that if we have n different outcomes in a sample space, and we label them O1, O2, O3, all the way to ON, so they're n different things, and they start with 1 and they go to n. Then remember that the sum of all the possible outcomes must equal 1, or the probability, if you add up all the probabilities together, they must equal 1. That should say the probability of all possible outcomes should equal 1. So if you add them all up, you should equal 1. And what I wanted to use this picture for is, remember that if you have an event and its complement, it divides the sample space into two distinct pieces, and it covers the whole sample space. Hold on, my pen's not working. Oh, wait, there it goes. This is my sample space. And if something's in A, it's not an A complement. If something's in A complement, it's not an A. Keep in mind, they don't have to be the same size spaces. So this one, A is a lot bigger than A complement. It doesn't matter. They don't have to be the same size. But the point is, if this is the whole sample space, then the probabilities have to sum up to 1, which means that the probability that A happens plus the probability that A doesn't happen, or A complement happens, has got to equal 1. So think back to that rain example. The probability that it rained, or was going to rain, was 60%. The probability that it wasn't going to rain was 40%. And that adds up to, voila, 100%. Like, that's not surprising. And so this is where the rule of complements come from. The probability that an event happens plus the probability it doesn't happen has got to equal 1. And that's just true. As long as you have a true complement, that's true. Okay. Now let me do a little bit of basic algebra real quick to show you where our rule of complements is coming from. I'm going to subtract the probability that A happens from both sides of this. I can do that. It's an equation. I'm just doing some algebra here. And if I do that, then this cancels out, and I'm left with the probability that A complement happens is equal to 1 minus the probability that A happens. So since the probability of A and A complement have to sum to 1, then I could subtract the probability of A on both sides and get this nice rule, which is on this page, a little bit neater. The probability that A complement happens is equal to 1 minus the probability of A. This is really, really nice, because oftentimes when we're doing probability calculations, one of these is going to be a lot harder to find than the other. So sometimes the probability that A complement happens is going to be hard to calculate, but the probability that A happens isn't hard to calculate. So you just find this thing and then subtract it from 1, and you find the other thing. It's like, we know that the probability that it's going to rain is 60%, like we did this earlier, and we kind of have a basic, like, conceptual understanding that we know that if the probability it rains is 60%, we know to just subtract that from 100% to get the probability it doesn't rain. That should be a minus sign. And we get the probability it doesn't rain over here. Like we kind of know that, and that's going to be how probability works once we introduce this idea of the complement. So this looks like it's going to be a very similar example. According to the Wall Street Journal, 40% of cars sold in recent years were small cars. What's the probability that a randomly chosen car sold that year is not a small car? So you see this word not. You got small car and you got not a small car. So the probability you have not a small car is equal to, I'm using the rule up on the top of the screen, is 1 minus the probability that you have a small car, which is 1 minus 40% or 60%. We usually call probabilities decimals, so we're going to do 0.6. But you see how quick that is? Again, intuitively, like it makes sense, but you're going to find a few more like confusing sounding problems where you can just find the complement by subtracting it from 1. Subtract the probability from 1, and you get that. So this is a very, very powerful rule. Let me show you another one with a bigger data set. I want to try to convince you that you want to use this rule of complements as much as you can. So here's a survey of a sample of 1,000 employees at a company, and we've recorded the age of each, and we're going to find the probability of a randomly choosing an employee that is not between 25 and 34 years old. So here's the word not again. I'm going to use my rule of complements to get this probability. So the probability that we're not between 25 and 34 is going to be 1 minus the probability that we are between 25 and 34. So I haven't even done any math yet. I just applied the complement rule. The next thing I need to do is find out what is this probability. Well, here's a frequency distribution, and I have the number of people who are in that age range, and I have the total number here. So the probability that I fall between 25 and 34 is going to be 366 over 100. 1,000. And that ends up being 634 over 1,000, or 0.634. And see, that was quick. That was quick. Now, what we also could have done is we could have said, okay, well, not between 25 and 34. Well, that's going to be all these guys and this guy, and we need to add all those up, divide by 1,000. Can we do that? Yeah, you can do that, and you'll get the same answer. But my way was faster. So you can find it not using this formula, but this formula helps you out because it's quick. And finding the probability of people in this bracket is a lot easier than just trying to adding up all these numbers of people who aren't in that bracket. And sometimes it's even not possible to do it a brute force way, and you got to use this formula. So all that is to say, this formula is going to be really helpful to you. So remember that complements are a thing. Try to recognize a complement when you see it. Sometimes the word not will give it away. So it's not this thing. So if it's not, then it's a complement. And try to use this rule to your advantage. It's going to help you solve some more challenging problems.